Good morning, sir.
Good morning. So, are there any questions? Anybody want to ask any question, any doubt?
Hello, sir.
Yeah,
Sir, my question is from lecture 18, in which you have told,
lecture 18.
yes,
So, you want me to open that file or you can ask
no,
without that?
it is simple one only.
Okay,
You have said that while evaluation of stresses, we cannot write stresses as del sigma is equal to Cti minus 1 into d epsilon.
yeah,
So there you have said that yield criteria is not satisfied. But
yeah.
sir, while we are evaluating Ct, we are calculating lambda, and while calculating lambda, we are satisfying the yield criteria f is equal to 0, df is equal to 0.
DF, yeah. So, but see, when we are evaluating CT, so finally, if you see CT is a function of stresses, and actually for the stress evaluation, though, that should involve the current stresses. But CT, what is available directly is the corresponding to stresses in the previous iteration. So that is why it will not satisfy the although we derived the expression for lambda from df equal to 0, but ultimately it comes out as a function of stresses. And when we are evaluating CT, we are evaluating CT corresponding to stresses of the previous iteration. So that is why it will not satisfy the yield surface in the current state, and therefore you express all the incremental stresses in terms of lambda or incremental equivalent incremental plastic strain, and then get your stresses.
Okay, sir. I mean, so whatever whatever the elements are in CT, we are evaluating using the stresses of previous iteration. That's what you are
Yeah,
saying.
yeah.
Okay.
Any other question, anybody? Okay, then let me start. Is my screen visible?
Yes, sir.
Okay. So we are continuing with the viscoelasticity. So now last class I was talking about, the last thing I discussed was the Prony series. So I had said that no, Prony series is corresponding to the extension of the standard model, and so I know I had said finally that Young's modulus as a equivalent Young's modulus as a function of time is given by E infinity plus summation I going from 1 to n ei e to the power minus t upon tau I. So this is what we call as Prony series. So now there are a number of constants in this. So for example, if you take the four Maxwell elements, this is coming from your Maxwell elements in parallel with this elastic element of the Young's modulus E infinity. So suppose if we have model with four Maxwell elements, so then if you look at the material constants which we need, the material constants. So because there are four elements, so material constants, so you will have E infinity is a material constant, and then this E1, E2, E3 and E4. If now you have four elements, four Maxwell elements, then these are the Young's moduli of each Maxwell element, and then the relaxation constants tau 1, tau 2, tau 3, tau 4. So these are the material constants. We need this to represent the constitutive behavior of the material. So how do we get these constants? So one of the approach is to use the data fitting in the stress relaxation curve of the material, and then find out these constants through data fitting. So that's one. Of course, there can be other frequency based approaches also. So these constants are determined from stress relaxation curve of the material. So that means, you take a uniaxial sample of the material and apply a constant strain in that. So you know the strain, and then you record the stress as a function of time, or load as a function of time, and then divide by the cross sectional area, so you get the stress as a function of time. And then the stress relaxation response in terms of this. So you can find out, based on this you can actually fit the data and get all these constants: infinity, e1, e2, e3, e4, tau 1, tau 2, tau 3, tau 4. So depending on how many elements you take, you have to determine those many constants. So far what I discussed is actually the response under uniaxial state of stress. So under uniaxial state of normal stress. So similarly, if you are taking a sample and subjecting it to the shear stresses, so you can get the shear modulus or modulus of rigidity. So similar thing you can do for that. So similarly, modulus of rigidity can also be written in terms of Prony series. Modulus of rigidity or shear modulus. So the same kind of an expression you can derive for this. The same model. Only thing in place of Young's modulus, you have shear modulus. Other things are same. So you will have G infinity plus summation I going from 1 to n gi e to the power minus t upon tau I. And same thing you would do for the bulk modulus. Bulk modulus will be similarly given by no, you can say kt is equal to k infinity plus summation I going from 1 to n ki e to the power minus t upon tau I. In usually these relaxation constants tau i's are same, but they can also be different, no, under the normal stress, under the shear stress, or under the mean stress pressure. So now for each of these cases we have already seen that the stresses are, no, the sigma we have already seen that using Boltzmann integral, sigma at any time t is 0 to t e t minus t dash into d epsilon by dt dash into dt dash. So it's given by this integral. Similarly, when you look at the shear stress, so tau t, tau I am denoting for shear stress, and this tau is the tau with a subscript is the relaxation constant. So this difference you have to keep in mind. So this tau 2 will be given by integral 0 to t g t minus t dash into d of, now the shear strain will come dt dash into d gamma by dt dash into dt dash. And similarly, if you look at the mean stress, sigma m, which is the mean stress, sum of mean of all the three normal stresses. So integral 0 to t k t minus t dash into d epsilon volumetric strain by dt dash into dt dash. So here this is mean stress, and this is volumetric strain. Yeah, so this is no, you can write now. So this is for the uniaxial case. Now, how do we extend it for the multi-axial, the three-dimensional state of stress? So let me know this can the extension is actually straightforward. So no, and then I will emphasize more on the linear isotropic viscoelastic solid. So first I will start with the general relationship. So let us say that, so now I'm going to talk about this general constitutive relation for linear isotropic viscoelastic solid. So the way we have extended now, if it is a 3D case, we can straight away extend. So sigma as a function of time. So all the six components of stresses can be written as integral 0 to t, and then you will have a constitutive matrix C evaluated at t minus t dash. So this into the derivative of strain tensor with respect to t dash, so dt, the epsilon by dt dash into dt dash. So this is exactly similar to what we are writing here. Now in place of a single stress component, the all the components of stress are there, and then in place of E we have the constitutive matrix as a function of time, and then we have in place of a single strain, here we have this all the six components of strain. So that is how you can write it. And let me specialize this to isotropic viscoelastic solids. So before I can do that, let me tell you that for if we want to look at the relationship between the deviatoric stress and the deviatoric strains and the mean stress and the volumetric strain, so for elastic case, so let me write that, and then based on that we can extend it for the viscoelastic solid. So first let me say that for deviatoric and volumetric elastic response. So if you want to you can of course derive from the general relationship for the this linear elastic isotropic solid. So I'm writing the results directly. So you have sigma xx d. So d you already know that we are using for the deviatoric stress component. So this is equal to, for the elastic solid, epsilon xx d. And so similarly you have all the three these deviatoric, normal deviatoric stresses 2z epsilon yyd, and sigma zz is 2g epsilon zz. And similarly you can write the shear stresses. So you will have tau xy as g into gamma xy, that you already know for the isotropic solid. If we use in tensorial shear strain, so then we will have 2g into epsilon xy, you can write. So 2g can be common in the normal and the shear components. So tau yz is also similarly equal to g times gamma yz, and tau zx is g times gamma zx. And if you look at the mean stress,
Sir,
yeah,
sir, how are we replacing E with 2G directly? Like, is
we are
mu
not
zero?
replacing no, we are not replacing E with 2g. This is the deviatoric components. So when you, we are not replacing, it can be any new value. Only thing is the deviatoric stress is for the linear elastic isotropic solid. Deviatoric stress is, so now if you write the stress strain relationship for a viscoelastic, no, for a no, a linear elastic solid, and then try to get the relationship between the deviatoric stress and deviatoric strain, so it comes in this form. So it is not that we are replacing E by 2G. This is the exact relation without any assumption on Poisson's ratio.
Okay, sir.
Yeah. So similarly, the mean stress is which is mean of all the three normal stresses. So sigma yy plus sigma zz by 3. This is actually equal to bulk modulus k times volumetric strain, that is epsilon xx plus epsilon yy plus epsilon zz. So this is what we call, let us say, the volumetric strain epsilon v. So now these are the relationship for the elastic case, and now we can if we have the the shear modulus using Prony series as a function of time, we can extend these relations for the viscoelastic solid. So now in that, let me assume that the deviatoric response is viscoelastic, but the relationship between mean stress and volumetric strain is still linear elastic. Although no, you can have both viscoelastic, but for the time being, let me assume that deviatoric response is viscoelastic and volumetric response is linear elastic. Linear elastic. So for that, so if material depicts viscoelastic deviatoric response and elastic volumetric response. So then we can see, now if I want to write the the stress components as a function of time, so say for example sigma xx as a function of time. So we can extend the same relationship what we did for the uniaxial case, we can extend the same thing. So it is integral 0 to t and then 2 g t minus t dash, and this into basically the deviatoric strain. And deviatoric strain, how do we get? So we get d epsilon xx by dt dash minus 1 upon 3 into d epsilon v by dt dash. So get the deviatoric strain, you subtract epsilon xx minus mean strain, which is volumetric strain, by 3. So you can write it like this into dt dash. So this is the extension of directly this relationship for the viscoelastic case. So the same, we have g as a function of time for viscoelastic case, and then this is the deviatoric strain is written here like this. So this will give you the deviatoric stress, plus we will have to add the mean stress to get the sigma xx, because sigma x deviatoric stress is sigma xx minus mean stress, and I'm saying that the volumetric response is elastic, so that you can write the mean stress as k times volumetric strain epsilon v. So as you see, this part is basically volumetric part, and this entire thing, if you look at this entire thing, this is deviatoric part. So
Hello,
this is
sir.
how, yeah.
Sir, like, can a material behave differently in volumetric and deviatoric domains?
Yeah, it is possible. Material can behave differently. Volumetric response can be elastic, or even if some viscoelasticity is there, it would be very less. Time dependence would be very less. Whereas in the deviatoric part of the shear components, it will behave as a viscoelastic material. So this is possible. Of course, you can also have the volumetric response also as viscoelastic. So then you can add no this integral as 0 to t k t minus t dash into d epsilon v by dt dash into dt dash. So that it is time replaced by that. So, but this is, yeah, possible. I know you material depict this kind of a response. So similarly, you can write all the components of stresses. Similarly, sigma yy as a function of time t would be integration 0 to 2 g t minus t dash into d epsilon y by dt dash minus 1 upon 3 into d epsilon vy dt dash into dt dash and plus k into epsilon v. And same way sigma zz at any time t would be integral 0 to 2 g minus t dash into d of epsilon zz by dt dash minus 1 upon 3 d epsilon v by dt dash into dt dash plus k into epsilon v. So this is how it is easier to write this relationship for the linear viscoelastic isotropic solid. And of course the shear stresses tau xy as a function of time would be integration 0 to 2 g t minus t dash into d gamma xy by dt dash into dt dash, and tau yz, so tau yz at any time t will be equal to integral 0 to t g t minus t dash into d gamma yz by dt dash into dt dash, and tau zx integral 0 to t g t minus t dash into d of gamma zx by dt dash into dt dash. So this is straightforward. I just said some of you asked whether the is it possible to have deviatoric and volumetric responses behaving differently. One is viscoelastic and another is elastic. So it is possible, but suppose if the volumetric response is also viscoelastic, so then we can then we also need the Prony series constants for the bulk modulus, similar to Prony series constants for shear modulus, and then we can write the stresses using Boltzmann integral. So if volumetric response is also viscoelastic, then we will have I will just write one component and then you can write similarly the other component. So sigma xx in that case as a function of time would be integral 0 to t 2g t minus t dash into d of epsilon xx by dt dash minus 1 upon 3 of d epsilon v by dt dash into dt dash, plus now the volumetric part is also viscoelastic, so 0 to t k t minus t dash into d epsilon v by dt dash into dt dash. So this is how you can write for that case. So then you need Prony series for g, you need Prony series for k to write this. So similarly you can write the other components of stresses. The shear stresses would of course be same. So now you can write similarly sigma yy as a function of time, sigma zz as a function of time t, and of course the shear stresses, for example tau xy at t will be same, summation integration 0 to t g t minus t dash into d gamma xy by dt dash into dt dash. So similarly the other stresses tau yz t you can write in a similar manner, tau zx at t you can write in a similar manner. So now of course in this model, if you see, as I said, there are two Prony series, one for g, another for k. So where g as a function of time would be g infinity plus summation I going from 1 to n gi e to the power minus t upon tau I, and kt would be equal to k infinity plus I going from 1 to n ki e to the power minus t upon tau I. So this is what you will have as the constitutive relation for the linear elastic isotropic case for three-dimensional state of stress. You will notice here when we look at this Prony series either for E, G or K, so if you look at t equal to 0, the modulus is going to be g infinity plus summation I going from 1 to n gi. So, and whereas at t equal to infinity, this term will go to 0. So the modulus at t equal to infinity is going to be g infinity. Similarly, bulk modulus at t equal to infinity would be equal to k infinity. So that is why this term is used as g infinity. That is like the modulus at t equal to 0. So the contributions from all the viscous element will not be there. Only elastic part will be there in the the standard model, extension of the standard model. So that also you can relate what is the meaning of g infinity and k infinity, and what is the initial modulus. Initial shear modulus is g infinity plus summation gi. Similarly, initial bulk modulus would be k infinity plus summation ki at t equal to 0, and at infinity these are the values. Now we need to look at the no ultimately we want to develop the element level governing equation. So how the finite element formulation is done for this. So again I'm going to start from the principle of virtual work. Principle of virtual work can be written for any problem, so that is why we actually start with that. So now let me look at the finite element formulation. So it is similar to what we have already earlier discussed, finite element formulation. So now we start with the principle of virtual work. So as per that, we have this integration over volume, we have variation in strain. So we have already introduced all these quantities. So variation in strain delta epsilon transpose into sigma dV. So we are using the wide notation. So we are representing the strain tensor by the 6/1 vector, and stress tensor also by a 6/1 vector, and minus the integration over volume again, the potential virtual work of body forces. So we have delta of UVW transpose into body forces FBX, FBY, FBZ into dV minus the virtual work of traction acting on the surfaces. So that would be delta of UVW and into TNX. This is transpose TNX, TNY, TNZ ds, and this is equal to 0. So you already know I'm going to finally look at in light of viscoelastic material how this relation finally gets modified. So but for the first time being, let us just get into the final element level governing equation form. So for infinitesimally small deformation gradient, this would be epsilon would be b into dE, and the displacement vector UVW will be equal to H transpose into dE, and delta of epsilon would be equal to B into delta of dE. So now in this you already know the notations. We are making use of the same notation. So B is strain displacement matrix, strain displacement matrix, and H is the interpolation matrix. Yeah, so now based on this, if you substitute these approximations within an element, and then take delta dE as arbitrary, delta dE is arbitrary. So if delta d is arbitrary, then you can get finally the element level governing equation from this relationship. Based on these can be written as integration over volume. And now you keep in mind that this is written at a particular time instant t, although I have not written explicitly time t, but it is at any time instant t. So B transpose into sigma dV minus or equal to, you can write integration over volume H transpose into FB, the body force vector, plus integration over surface H transpose into traction vector ds. So you can write the element level governing equation in this form. And as I said, this is at a particular time instant t. So for a viscoelastic solid, the problem is time dependent. Although you may not consider the inertia forces, it's like a quasi-static problem. But because the material response is time dependent, the stress strain relationship is time dependent. So the problem is a time dependent, even without considering inertia. Of course, you can have a dynamic problem in which viscoelasticity is there. So then you will also consider the virtual work of inertia forces. So now the problem is, what we have at hand is problem is time dependent. So now the problem is time dependent. So how do we solve it? So for the solution, now the entire time duration we divide into a number of steps. So say we start at t equal to 0 and then go to delta t, the next time instant. Then we go to, from delta t we go to 2 delta t, where delta t is time increment. Then we go to 3 delta t. And like that, we could have gone up to the, say, the nth time step, and then from nth time step to n plus 1th time step, and then we continue like this. So this would be n into delta t, and this would be n plus 1 into delta t. So now, so as far as the solution is concerned, we are going starting at t equal to 0, going to 2 delta t, then delta t, then 2 delta t, then 3 delta t, so on. So we would have reached up to tn, and then we go to from tn to tn plus 1. That is from n delta t to n plus 1 delta t. So this is how the entire problem is. So now how we can do, this is basically, if you look at the stress, so we can write the stress also as a, a stress in the previous time instant, and the increment in the stress. So for this we can write that stress at any time instant t n plus 1 can be written as sigma Tn, that is at nth time instant, and plus the incremental stress from Tn to Tn plus 1, whatever is the increment that we add into this. So now if you based on this relationship, you can write the element level governing equation as integration over volume B transpose into, now because see, we would have solved the problem up to Tn. When we are going from Tn to Tn plus 1, we would have solved problem up to Tn. So sigma Tn would be known to us, but delta sigma is an unknown. The increment in the stress from Tn to Tn plus 1 is an unknown. So you can keep that on the left hand side. So you can write that as B transpose into delta sigma dV, and the right hand side, this term goes to the right hand side, so you get minus integration over volume B transpose. We are basically substituting in this approximation and taking the known quantity to the right hand side and unknown to the left hand side. So you can write this as B transpose into sigma at Tn dV, and plus you will have integration over volume, then you will have H transpose into FB dV plus integration over surface H transpose into Tn ds. So this will be the the element level governing equation once we make use of this relationship. Now we have to, ultimately what we are interested in is to express this delta sigma in terms of the incremental strains from Tn to Tn plus 1, and of course this will also be in terms of the stresses in the previous time step. So now let's look at what this delta sigma is. So for the general three-dimensional case, delta sigma is delta sigma xx, delta sigma yy, delta sigma zz, delta tau xy, delta tau yz, delta tau zx. So this is now what this delta sigma xx is the difference in the stress at Tn plus 1 and Tn. So if I look at just one component, so one component means, let me just look at delta sigma xx. So this will be actually equal to sigma xx at Tn plus 1 minus sigma xx at Tn. So this is what it would be. And from the Boltzmann integral, we already know the expressions for this sigma xx at Tn plus 1 and sigma xx at Tn. So you can write this delta sigma xx is equal to, the first term would be, because it is the stress at Tn plus 1, so the integration limit would be 0 to Tn plus 1, and then 2g, we are taking now as if the solid is a linear elastic, linear viscoelastic isotropic solid. So 2g Tn plus 1 minus T dash into d of epsilon xx by dt dash minus 1 upon 3 into d epsilon v by dt dash into dt dash. Now let me first write the, I'm again assuming that the deviatoric response is viscoelastic and volumetric response is elastic. So let me first write the integral term. So then we will have minus the contribution from this term. So that is the stress at Tn. So the integration would be from 0 to Tn, and then 2g, T is Tn. So Tn minus T dash, and then you will have d of epsilon xx by dt dash minus 1 upon 3 d epsilon v by dt dash into dt dash, plus of course the volumetric part. So that would be k into volumetric strain at Tn plus 1 minus volumetric strain at Tn. So this is what no your delta sigma xx is going to be. But no, we want to express this in terms of incremental strains, delta epsilon xx, delta epsilon v, and so on. So how do we do that? So for that, no, we need to expand this and work out. So let me kind of uh, rewrite this expression. So if you look at this, integral 0 to Tn plus 1 can be written as integral from 0 to Tn and then from Tn to Tn plus 1, so that we
Sir,
can bring in incremental strains into this. Yes, please.
sir, in the second term of the integration where we have written to g Tn minus T prime
Yeah,
into del epsilon x by dt prime minus half minus 1 by 3 d epsilon v by dt prime. So sir, this
yeah.
part is like constant with time, this strain part.
No, this is not constant. The strain in general we are taking also as a function of time. They are functions of time, and that is why we are differentiating them with respect to T dash.
Yes sir, so like with them also, like we are differentiating them at time t equal to Tn, is it
Yeah,
like
we are
that?
differentiating at not time t equal to T n, at t equal to T dash.
Okay.
See, this
Okay sir.
epsilon xx is a function of t. In place of t, we write T dash. So epsilon xx is a function of T dash. Epsilon v is a function of T dash, and we are differentiating them at t equal to T dash.
Okay sir, understood.
Yeah, yeah. So now what we want is, in terms of, as I said, we want to write it in terms of integral. The differential changes in the strains. So we write delta sigma xx first time demonstrating for one component, and then you can write similarly for the other component. So as I said, this integral we can write from 0 to Tn and Tn to Tn plus 1. So the incremental terms are going to come from Tn to Tn plus 1. So we can write integral 0 to Tn to g. This will remain same. See, this Tn plus 1 will not change. So 2g at Tn plus 1 minus T dash into d of epsilon xx by dt dash minus 1 upon 3 into d epsilon v by dt dash into dt dash, and plus we will have integration from Tn to Tn plus 1 to g Tn plus 1 minus T dash into d of epsilon xx by dt dash minus 1 upon 3 into d epsilon v by dt dash into dt dash. So the first term, this particular term, this term is split into two terms, and then of course we have the third one is integration 0 to Tn, and that is 2g Tn minus T dash into d of epsilon xx by dt dash minus 1 upon 3 into d epsilon v by dt dash into dt dash, and plus of course we will have the volumetric part, so which is k into epsilon v at Tn plus 1 minus epsilon v at Tn. So this is the terms. Now ultimately we are interested in writing this in the incremental form. So let us say, let me call this term as term number 1. I am going to look at each of these terms separately. I am going to simplify them. This is, let us say, term number 2, and this is, let us say, term number 3. So first let us look at this term, which gives you the incremental strains basically. So first we consider that actually term, second term. So first let us consider term 2. So for term 2, what we are going to do, that is this particular term, which is integral Tn to Tn plus 1. So for that, now to bring in that form, in terms of the incremental strains, we have to assume some strain variation between two time steps. So one thing what we want to do here is that this assumption we'll have to take, that say for example epsilon xx and so the other strains, and this side we have time t. So from this time instant Tn to time instant Tn plus 1, we are going to assume that the strain variation is linear, and let us say the slope of this curve is Rx, and at any time we have here T dash, and same thing of course we assume for the volumetric strain, although the volumetric strain is straightforward. No, that is that doesn't involve no, the time integral for this case. So if you take the volumetric strain and time t, so that is also assumed to be linear. So at Tn and Tn plus 1, and slope is, let us say, is Rv, and then you have some time instant T dash. So this is the assumption we are making, and this the accuracy of the result then would depend on delta t. So if we take smaller delta t, this assumption would be approximately valid. So for subsequent derivation, we are going to make this assumption that the strain variation is linear between Tn to Tn plus 1. So between different time steps, it is going to be linear, but the slope would be different. So say Tn minus 1 to Tn, there would be different slope. Tn to Tn plus 1, there is a different slope, but in between Tn to Tn plus 1 or Tn minus 1 to Tn, this is linear variation. So based on this, you can write epsilon xx at say Tn plus 1. If you want to write, it would be epsilon xx at Tn plus Rx slope into delta t. If you want to write this epsilon xx at any time T dash, so that would be equal to epsilon xx at Tn plus we will have Rx and then T dash minus Tn. So epsilon xx Tn is the strain at this time instant, and then we want at this time instant, so we just add this increment, so that would be Rx into this time interval. So similarly epsilon v at any time T dash would be equal to epsilon v at Tn plus Rv into T dash minus Tn. So yeah, this is the assumption we are making, and this is necessary to get the proper incremental form of stress relationship between the incremental stress and incremental strain. So now let me look at the second term.
Sir, delta t we are considering it to be small, right?
Yeah, delta t we are considering it to be small.
Okay.
And in the subsequent derivation, I am also going to assume that throughout this time duration, we are keeping the same delta t. That is the case most of the time, but you can have different delta t in different time intervals, so then you have to take care in the equations accordingly. But I am going to give you the derivation for uniform delta t throughout the time duration. So second term, now if you look at, we can write it as the integral from Tn to Tn plus 1, then 2g, and we have Tn plus 1 minus T dash, and now we know this epsilon xx T dash is this, so its derivative with respect to T dash is going to be simply Rx. Now using this relationship, you look at epsilon xx by t d epsilon xx by dt dash is simply going to be Rx. So I will have here Rx, and similarly the d epsilon b by dt dash is going to be Rv. So we have minus, of course, 1 by 3. So into Rv dt dash. So this is what you will have this. And now within that time interval, because this integration is from Tn to Tn plus 1, Tn to Tn plus 1, this is a constant term. So you can write this as, take out of the integration sign, so Rx minus 1 upon 3 into Rv, and then you have integration from Tn to Tn plus 1 to g, and Tn plus 1 minus T dash into dt dash. So this is what you have. Now we already know, using Prony series, we know already the expression for gt. So we already know, so we are going to substitute that in this integral and then bring in the the proper incremental form. So we know that gt equal to g infinity and summation I going from 1 to n gi e to the power minus t upon tau I. So now if you want to write g at Tn plus 1 minus T dash, so that would be equal to g infinity plus summation I going from 1 to n, and then we will have this gi e to the power, now in place of t we are writing Tn minus T dash, so we will have minus Tn plus 1 minus T dash upon tau I. So this is what you will have this. So now if you look at the second term, again, now if I look at this, the second term, so second term we can write it as, now this 2 also we can take out of the integration sign, this 2, so we can write it as twice of Rx minus 1 upon 3 into Rv, integration from Tn to Tn plus 1, and then you have now put the now the value of this g at Tn plus 1 minus T dash. So that is your g infinity plus summation I going from 1 to n gi e to the power minus Tn plus 1 minus T dash upon tau I into dt dash. I hope if you are having any doubt, you can please ask. So these are the straightforward derivations, but you should understand that. So now if you integrate, so we will get this, of course, 2 into Rx minus 1 upon 3 into Rv will be there. And now when you integrate, so the first term is a constant term. So the integration would be g infinity into Tn plus 1 minus Tn, which is delta t. So the integration of the first term is going to be g infinity into delta t. And the second term, when you do the integration, you are doing the integration with respect to T dash. So you can see that the integration of this term is, of course, summation sign will be there, I going from 1 to n. You will get gi into tau I, and so this is gi into tau I. Now you can just do the integration of this term with respect to T dash and put the limit t going from Tn to Tn plus 1. And if you do this integration, you will get gi tau I, and then 1 minus e to the power minus delta t upon tau I. So this is what you will get. There are two brackets over here. So this is what you will get. And then what we can now do is, now we can write this relationship. So now if you look at, I can take this delta t outside. So if I take it outside, so here I will have the Rx into delta t would be delta epsilon xx, Rv into delta 2 will be no delta epsilon v. So I can write this as twice of delta epsilon xx minus 1 upon 3 into delta epsilon v. And this, and then we will have inside the bracket we will have this g infinity, and the second term, because I am taking the common throughout, so we will have I equal to 1 to n, and then gi tau I upon delta t, because in the second term there is no delta t, but we are multiplying and dividing by delta t, and the one delta t we are taking common out, so we will get this into e to the power minus delta t upon tau I. So this is how you can write finally the second term. So the the good thing is that we are able to express the second term in terms of increments in the strain. That is what you see over here, and of course this term. So we are able to express it like this. Now let's look at the first and third terms. Now if you look at the first and third term, both are integration from 0 to tn. So this is integration 0 to tn, this is integration 0 to tn. Only difference is that in this we have tn plus 1 minus t dash, g is evaluated at tn plus 1 minus t dash, and this integral it is evaluated at tn minus t dash. So that's the difference. So now let's look at these first and third terms. First and third terms. And let us say whatever we have over there, let us call it as delta sigma xxn. Why I am saying delta sigma xxn is because when you look at this, so this first term is also contributing to sigma xx, third term is also contributing to sigma xx. Both of them are integration from 0 to tn, but one is tn plus 1 minus t dash, and other is in the integration we have tn minus t dash. So let us denote this difference, the difference of first and third term, basically. So let me say that the first term minus third term, let it be denoted as delta sigma xx n. So then delta sigma xx n, as per the definition, is integration 0 to tn, and then you have 2, and there is both are integrations from 0 to tn, so we can write that as 2 into g evaluated at tn plus 1 minus t dash minus g evaluated at tn minus t dash, and then into, of course, here you will have d of epsilon xx by dt dash minus 1 upon 3 into d epsilon v by dt dash into dt dash. So this is how the, and no, you please stop me if you are not following any step over here. So this is how we can write the difference first term minus third term. We are denoting that by delta sigma xxn, and that delta sigma xxn can be written like this. So from the definition of first and third terms, you can simplify this. You can d epsilon xx by dt dash minus 1 upon 3 d epsilon v by dt dash can be taken in common. So you can write it like this. Now we want to perform this integration. So see, this is the basically the integration from 0 to tn, and for this we want to derive some kind of a recursive relation, so that we don't have to store the stresses and strains for all the time steps. If we can derive some kind of a recursive relation, so if we know this quantity in the previous time instant, and then we should be able to, just using the previous time instant and the values for the current time instant, we should be able to calculate this. So that is what we want to do. Otherwise you require to store the values at all the time instances. If you can do that, then it is straightforward, you can do this, but we want to avoid that, so we are writing it like this. So now you can write this delta sigma xxn, substitute the value of g tn plus 1 minus t dash and g tn minus t dash. So we will have integration 0 to tn and then 2, and then we will have, now see, if both have g infinity, this also has g infinity, this also has g infinity, so g infinity minus g infinity will cancel out. So only these summation terms will remain there. So we will have I equal to 1 to n, and then we will have gi e to the power minus tn plus 1 minus t dash upon tau I. So that is, this term will be there, minus again summation I going from 1 to n gi e to the power minus tn minus t dash upon tau I, and into, of course, here you will have d of epsilon xx by dt dash minus 1 upon 3 d epsilon b by dt dash into dt dash. So you come here. So yeah, this is what you actually get. So now I think the requires the further approximation. So what you can do is, now to derive the recursive relation for the entire quantity delta sigma xx at n, we cannot get the recursive relation, but for the ith term, because it is involving this summation and this summation. So for the ith term we can write a recursive relation. So in this itself, let us consider contribution of ith term in the series, and let me denote that as delta sigma xx at step n comma I. So we are taking ith term from this for this delta sigma xx n, and of course superscript n is used because this involves the integration from 0 to tn. So this will be equal to twice integration 0 to tn, and then we will have gi and now you have both, we can take this gi as also common, so we can write as integration e to the power minus t n plus 1 minus t dash upon tau I minus integration minus e to the power minus tn minus t dash upon tau I, and then into, here you will have d of epsilon xx by dt dash minus 1 upon 3 into d of epsilon v by dt dash, so into dt dash. So this is what you can actually write this. And now I think there are some simplifications, so I will discuss that in the next class. So I want to stop here. In the next class we will complete this the basically the further, the final recursive relation. So we will get the relationship between delta sigma xx n I and delta sigma xx n minus 1 I, and in terms of some incremental strains. So that is what we want to derive. So we will continue in the next class. I want to stop here today. So yeah, if you have any questions and doubts, you can ask. Yeah, any question, any doubt? You can try yourself, you can try doing the deriving the recursive relation. So getting the relationship between delta sigma xx ni delta sigma xx n minus 1 comma I, and some incremental strains from n minus 1 to n. So you try doing that, but I will of course finally derive in the subsequent class. So yeah, any questions, doubts, anybody?
Sir,
Yeah,
sir, the Rx and RV for the delta time step, sir,
yeah.
delta T time step, sir, will those be same for each and every time step? Like, but
No, they will be different. So they are going to be different for different time instances. So when we have
so when
written
we
delta,
try, so now when we try to find this recursive relation, we
yeah,
require some other constant.
yeah, they will be, yeah, some other delta epsilon xx and delta epsilon v. Anybody else? Any question, doubt? Okay, so if there are no questions, I'm stopping here. Thank you all for your attention, And please go through this, and if you have doubts and questions, you can also ask in the next class. So I'm stopping here. Thank you all for your attention.